This is a figure from this 2013 seminal work on wide field high resolution Fourier ptychographic microscopy by Jung, Horstmeyer, and Yang. Here we are comparing imaging of a pathology slide in the lower center with a 2x objective, and right next to it the same slide with a 20x objective, and you see the dramatic increase in resolution. This little bar here is 10 microns, so we're seeing well down to micron scale resolution. The colored reconstructions in B, C, E, and D are all reconstructions with Fourier ptychographic illumination. What's being done here is this is structured illumination. The object is illuminated from a variety of different directions with different plane wave illumination structures. And then those diverse images are captured through a single 2x objective to low resolution objective at the lower center, but then combined to create a high resolution image. So with ptychographic microscopy, we achieve two things. One is we're able to recover the coherent field. So we've got a phase and amplitude image of the field rather than just a amplitude image. And second, something that's being done here for aperture synthesis to improve the resolution beyond the resolution you can get in a single aperture. Let's talk about how that works. Computational imaging. Episode 39, Ptychography. Over the last several episodes, we've discussed how sensitive coherent imaging systems are to the phase of the object. We've seen that if we shift the position of the imaging system, we induce a phase modulation on the object as measured, and that phase modulation corresponds to a shift in the Fourier space of the object as observed at the aperture. Here we see an experimental system developing this approach. We have a 4x4 array of cameras, each with a 25mm focal length lens, and each shifted somewhat in position. And they're observing objects that are placed on a spatial light modulator shown here. And what we would expect to see because of this phase modulation is that the cameras see somewhat of a different image of the object because there's interference between local features in the object. Here's an example of what you see. So we put this pattern onto the spatial light modulator, and this is the 4x4 array of images as observed. And each image, of course, is a radiance measure, but because of this phase modulation, we see different speckle patterns, essentially, on the object. Using the techniques that we'll talk about today, you can take this 4x4 array of images and recover the phase and amplitude of the object field distribution and get a resolution that exceeds the resolution of any one of the individual apertures. That's shown from the paper that was referenced in the second slide here, where we have a resolution target on the object. And what you see is that the resolution from the reconstructed phase and amplitude image using phase retrieval, as we'll talk about today, is greatly improved relative to the raw captured image. So let's talk about how this works. Episode 36 derived the coherent impulse response, which we derived by considering the field propagation from an input point at x0, y0, a distance z1, away from the lens, and then from the lens to a image plane, a distance z2 behind the lens, where we observe the variables x double prime, y double prime. So this is an impulse response from that x naught, y naught input point to the measurement plane, which is distributed with variables x double prime, y double prime. We considered this for the transformation between focal planes, but we also considered this impulse response under the thin lens imaging condition, in which 1 over z1 plus 1 over z2 is equal to 1 over f. This goes to 0, and this quadratic phase modulation in the pupil plane goes away. Of course, in episode 38, we talked about what if there's defocus, where we kept that term, but today we're going to assume that we're going to deal with a well-focused system, so we'll drop the defocus term, and now we see that the impulse response is proportional to the Fourier transform of the pupil function evaluated at spatial frequency x prime over lambda z2, which would be x prime over lambda f. So this is this Fourier transform part, so the integral here, but now out in front we have these quadratic phase terms, which we discussed in episode 37. Now, so this is quadratic phase modulation in the image place. This is quadratic phase modulation in the object space. So the impulse response is not shift invariant because we have the shift invariant part coming from the Fourier transform of the pupil, but we have this phase modulation in front. When we make measurements, we don't measure the coherent field unless we're making a holographic measurement, but typically we'll measure the irradiance of the field, in which case we take the magnitude squared of the integral of the object field against the impulse response. And now we see that that integral is not a shift invariant convolution because we have this quadratic phase modulation out in front. Okay, so this is our this we derived back in episode 37 in talking about that quadratic phase modulation, and we considered what happens when we shift the aperture. So let's say we shift the position of the camera by delta x, delta y, which would be in object space, or we shift the object by delta x, delta y, as shown here. Now we can expand the object position in terms of this shift. Now we're considering the object in the image space where we'd be working in demagnified coordinates. So we put the magnification into the shift. But now we can change variables, so we can get back to the object field in its image space coordinates, and then we substitute this x plus m delta into the quadratic form, and we get this form where we've got this linear phase modulation. We also have a modulation in the output object space, which goes away because we're taking the magnitude squared, and we have this quadratic phase modulation in the object space. Now, independent of the shift, this quadratic phase modulation times the object distribution, that's what we measured before we had the shift of the camera. So the effect of shifting the camera is to shift the image, certainly. So we see a shift in the impulse response. So we shift the camera, the position of the image shifts. But we also see that we put this linear phase modulation on whatever image that we measured prior to the shift. So f sub p here would be the image without the shift. And then we put this phase modulation onto that as we shift. So we're measuring the convolution of the object with a impulse response, but with a phase modulation. That phase modulation corresponds to a shift in the Fourier space that was observed, which we talked about in episode 37, that there's a shift in the bandpass. So we're looking at the object with a low bandpass, but shifting the bandpass. This idea of local measurements in the Fourier space or local measurements in object space corresponds to spectrograms, which we discussed way back in episode 36 when we talked about temporal holography. Spectrogram is a representation of the signal as it varies over space, or of the frequency of the signals that varies over space or varies over time. So it's a localized Fourier transform rather than considering over the full Fourier space. Back in episode 36, we considered spectrograms in the context of frequency-resolved optical gratings, frequency-resolved optical gating as a method for characterizing ultrafast pulses that are modulated by some kind of nonlinear interaction. We could look at the pattern of the frequency, the spectrum as a function of time, and by looking at the spectrum as a function of time, you get this local two-dimensional pattern that you can implement phase retrieval on to try to reconstruct the intensity and the phase of the unknown signal. Now we're going to consider spectrograms in the context of spatial imaging, which is ptychographic imaging. So ptychography can be considered typically in two different forms. Standard ptychography has the idea that we have a object field, f of x, y, and we consider the object field over a finite pupil. So we put a mask on the object field, and so we only consider the part of the object field, but we can measure now the Fourier transform of the masked object field. So we put a mask on the object and take its Fourier transform, and we can shift that mask around. Alternatively, we have the idea of Fourier ptychography, where we have a mask in the Fourier space of the object, and we consider the full-scale image of the object, but filtered by different masks in the Fourier space. We can make a sequence of spectrograms in both cases is we have a spatially local object with the full spectrogram, or a localized object in the Fourier space, and we measure its full image. But we're measuring effectively a spectrograph, a image in space or frequency, but keeping a frequency parameter. So here we have in Fourier ptychography the image of the object as a function of frequency. And in the case of standard ptychography, we have the Fourier transform of the object as a function of space. So in both cases, measuring a form of spectrograph. Now, today's episode considers a implementation of ptychographic signal analysis as uploaded onto the GitHub site that goes with this course. We're looking at this ptychography wavefront camera GitHub repository. We're going to consider this as an example object in our analysis. So we have our snake laying on asphalt, and we can take the Fourier transform of that image, which is shown here. So this is the image in this case is 512 by 512. We take its full-scale Fourier transform. Now in this case, these are complex objects. Of course, it's not a unipolar object necessarily. We could have a phase and amplitude at every pixel of the object. In this case, so we've assumed that the object is bipolar to get rid of the large DC that would otherwise be present. But still, the object is pretty smooth, so the Fourier transform is fairly well confined to a localized region. If we think about ptychographic sampling, what that means is we put a mask over the object. So the object covers all of this area, but we've put masks over the objects and taken the Fourier transform of the masked object. And for different regions of the object space, we see different Fourier transforms. So we're seeing spectrograph of the object as measured, the spectrum of that local region of the object. In contrast, if we look at Fourier ptychographic sampling, this square on the left is the Fourier space of the object. We put a mask in the Fourier space. So we take the Fourier transform of the object, mask the Fourier space, and inverse Fourier transform. You see that if the window is up off of center, we get high frequency. If the window is in the center of the Fourier space, we recover the low frequency image of the object. And here it's shifted to negative frequencies. Again, we're seeing the high frequencies depending on where the sample is taken. Now, in Fourier ptychographic imaging, we will take a lot of these spectrographs. So, we have these windows that you see here in the Fourier space. We can shift that window everywhere you want. And so one of the key things here is we're going to take overlapping windows in the Fourier space. We saw in our analysis of holographic imaging and phase retrieval that we need to make more than one measurement per reconstructed signal value to have a good shot at recovering the phase and amplitude of the image. In the case of holography, we oversampled by a factor of 4. Here, you'll find in Fourier ptychography that you want to shift the window in the Fourier space so that you have somewhere close to a 50% overlap in each shift, so that you oversample by a factor of at least 4 to 10 in this system. So now we have this set of spectrographs, and we use iterative phase retrieval, the same as was used in frequency resolved optical gating for temporal recovery. So the basic algorithm for recovering the phase and amplitude of the unknown object distribution is to take the measured low resolution amplitude, assign a random phase to it, take its Fourier transform, update the Fourier space just of that part of the spectrograph, and then inverse Fourier transform to estimate the image again. And then you have the phase in this new estimated region. You can keep the phase, but update the amplitude to its known value and iteratively proceed through this. Now, in the case of full-scale phase retrieval, we did this between the Fourier space of the image and the Fourier space and the image space, that we cycle back and apply some kind of constraint, typically a support constraint on the image or its Fourier transform. Here we have a support constraint for each measurement because we know that it's limited to just a specific object region or a specific Fourier region, so we only update the amplitude in the region that we've measured, but we don't operate on the full image in any one of these steps. This is repeated for each of the sub-images in the array. So you may take several sub-images and cycle through them to recover the phase and amplitude of the field. So the code that's on the GitHub site implements this for this test object. Here we've assumed various levels of number of photons per pixel, the maximum number of photons measured per pixel. And you can see as the number of photons per pixel is increased, the peak signal to noise ratio increases as well. So this method, by subsampling the Fourier transform and then measuring the magnitude squared of the object as band limited by a subsampled Fourier region, which would be the case when we have imaged the object through a pupil, where the pupil acts as the bandpass. That we enforce the consistency through regression with our measurements and iteratively recover the phase. Okay, so I invite you to go on the GitHub and play around with that. Now you could say, how well does this work? What are the limitations of this? So the key here is we're using local interference between pixels in the scene. So this is self-referencing phase retrieval, basically, that each pixel in the scene interferes with its neighbors, and as we change the relative phase of those two pixels, two adjacent features in the object, by translating the aperture or translating the object, or by changing the illumination on the object, we're changing the relative phase of pixels within a resolution cell, and through that modulation of the relative phase, we can recover their phase and amplitude of each individual pixel. You can model this process by considering, what is the impulse response for a single impulse or for multiple impulses. Here we're showing, for example, that we've got two impulses in the object space. Now, if it was a well-resolved system, what we would see, of course, is the impulse response for each of those two objects, or two object, impulses. But as those impulses get closer and closer together, we will have more and more trouble discriminating them. Now, this idea of analyzing imaging systems using the impulse response is something that we started in episode 37, and will continue throughout this episodes of this computational imaging system. It's just key technique to understand how the system responds to impulses or to pairs of impulses. For a single impulse, we've seen that the field that we would measure from a single impulse would be the impulse response due to the band limit and the Fourier transform of the pupil function. Here we've included the idea that the pupil function could have some defocus, so we have this impulse response from the pupil function, and then this phase modulation from shifting the aperture by some amount. For a single impulse, we just measure the magnitude squared of the impulse response when we make an irradiance measurement. So our measurement would look like this. Now this phase modulation goes away, so translating the aperture doesn't change the image for a single impulse. Of course, the position of the impulse in the measurement plane would shift, but the phase of the impulse doesn't change. So we can't really use Fourier ptychography or this shift to get any information about the phase of a single impulse or to super resolve its position. But now if we have two impulses in the input plane, then we have these impulses here we assume at position x0 and at position minus x0. As we shift, either by shift the relative phase of those two impulses, either by illuminating them with a wave at various spatial frequencies. So here we have u prime could be the x component of the wave vector of the illumination wave, or it could be due to the shift in the aperture. But we have a relative phase between these two impulses. We take the magnitude squared. Of course, we have the impulse due to each one of the exciting impulses individually. And then we have this interference term between the two impulses. So in the GitHub repository, there's a notebook looking at the irradiance that you would measure for impulses, two impulses imaged through Fourier ptychography for various impulse separations. Here at the upper left, we're assuming that the two impulses are separated by half of the area separation. If the illumination is such, or the relative position of the camera is such that the two impulses are in phase, you see this signal, but as you shift the illumination angle or shift the position of the camera, they'll go out of phase, and you'll see this destructive interference. And so by measuring the interference pattern as a function of the shift in the illumination pattern, shift in the position, you can back out what is the separation between these two impulses. If the impulses get further apart, then it becomes hard to see their interference. So here, if they're separated by 4 times the area separation, you wouldn't see any interference between them, and you wouldn't be able to use them you wouldn't be able to use that interference signal to back out what is the relative position of the two impulses. The key thing here, of course, is to think about what is the overall resolution of the system. What we're doing here, so this is a map basically of the Fourier plane of the object under test. And so, of course, we would expect if we could recover the coherent Fourier transform of the object over this full range, that the maximum spatial frequency, U max, is going to go like the position, the scale of this synthetic aperture divided by lambda times the f number, basically, and then the resolution that we would expect to achieve through this system should be basically lambda times the f number of the system. And of course, it could be lambda f number over 2 if we think about the x going from over the full aperture scale. So the same as what we'd have in a coherent system, but it's increased by a factor of the resolution is improved by a factor of A over X, where A would be the aperture of one of the sub-imaging systems. So it's a very, very useful thing that we've achieved here. There are other ways to do phase retrieval, as we've seen, but nice things about Fourier ptychography is, first of all, that the reconstruction algorithm is much more robust than if we had tried to do the full-scale aperture. People have used Fourier ptychography to recover gigapixel scale images, but in processing gigapixel scale images, the individual steps in the error reduction algorithm may require only working with megapixel scale images, and you just use several hundred or even thousand megapixel scale images, and you can recover a gigapixel image where any of the Fourier transforms that you're taking are all going to be on that megapixel scale. Another advantage of Fourier ptychography is that the interference between those 2 point sources we talked about occurs locally within each pixel, which means that the spatial and temporal coherence of the field only requires interferometric coherence within local regions of the image. Fourier ptychography has been used in a wide variety of situations. Mostly, the most successful uses to date have focused on microscopy. Here's a review paper by Konda, Lothar-Gehring, Zhao, Shu, Harvey, and Horstmeyer, where they look at a wide variety of different geometries and algorithms for Fourier ptychography microscopy, with the advantage being that you can use a low numerical aperture focal length and use structured illumination with different illumination angles to shift the Fourier space of the object and recover the full aperture. So this is done, in microscopy, typically with these LED arrays. But then and there, the success that you see is like you saw in the introduction in the first slide, that by using this kind of multi-angle illumination, people achieve reconstruction, 10x improvements in object resolution, which is very interesting and dramatic. And you see all these different geometries where this could be obtained with structured illumination from different directions being the originally successful approach, but lately people are using camera arrays that have this shifted Fourier space, like you saw in the second slide in today's discussion. And algorithms have also, of course, gotten a lot more advanced. Even if you use iterative phase retrieval, you would be wise to use deep image priors, like we talked about when we were talking about compressive diffraction tomography. You can do multidimensional reconstructions of the object if you build a multidimensional forward model. And of course, you're well advised to use neural regression to improve the image after processing. So that's our survey of ptychographic imaging systems. Next time, we're going to talk about what if we just want to make a camera that could measure the coherent field. And we'll use this approach for a ptychography. We'll talk about snapshot wavefront cameras and how we could recover the coherent field. So in this chapter, chapter 6 of computational optical imaging, we have talked about the use of optical elements in coherent systems and how we can form images. In chapter 5, we talked about how we can propagate the field, how we can measure the field with holography or phase retrieval, and how we use that to estimate multidimensional objects. What I hope that you take away from this is the feeling that increased sophistication in the modeling pays off in these systems. And one thing that is kind of the holy grail of this kind of system would be, could we make a sensor that just captures the coherent field, and then having measured the coherent field would allow us to backpropagate and estimate objects. And we'll talk about that in the next episode.